Welcome back. Today we are doing lesson 4.4, linear functions. Our standard is 8F1, solving linear functions, and our essential question is how can we model relationships between quantities?
All right, so you got two pieces of information to start in your notes. A linear function is a function in which a graph of the solution forms a straight line. So is this the part, graph of the solution?
That is true. You're writing it down.
And then a function can be considered either continuous or discrete. And we'll talk about what each of those means here in just a minute. But those are your two options when we are looking at a function.
More vocabulary words. Woohoo! Continuous data. Moving down in the notes, continuous data is, it can take on any value. So -2, 16, 25.
You could have decimals, you could have fractions.
We're not going to have any space between the data, and we're going to represent it when we graph it with solid lines. We're going to connect the dots.
Discrete data has space between the data values, so they're going to be represented by dots, so there might not be something that exists in between them. So think days of the week, Monday, Tuesday. There's nothing in between a Monday or a Tuesday. Those are discrete pieces of information. They're all separate from each other.
No line.
Then we won't connect those with a line since there's nothing in between those points.
Some examples. Continuous data could be the number of ounces in a glass or the weight of each separate chocolate chip.
Discrete data is something that can be counted. So the number of glasses in a cupboard. You couldn't have 3.5 glasses. It'd be 3 or 4 or 5 or whatever it might be. And then the number of chocolate chips in a bag. You can count how many are in each of those bags, but there's nothing in between those individual numbers you've counted.
You can determine if data that model real-world situations are discrete or continuous by considering whether all numbers are reasonable as part of the domain, so the x values.
All right, so you got a bunch of little blanks to kind of fill in as we go.
Yep. A, we're going to write an equation. We're going to leave those parentheses blank, and we'll discuss that in the next unit. So keep going with what we're doing. We're going to write an equation from the function box.
Okay. And then you're going to use your input values of -2 to 2 unless they're given to you. Then you're going to write out your ordered pairs. You're going to take your x and your y's and create your ordered pairs.
Then we're going to create a graph to fit the ordered pairs. So x is horizontal going across, y up and down, and then you're going to plot those points.
And then here's where the continuous or discrete comes in. If it's continuous data, meaning numbers could exist in between our points, we're going to go ahead and connect those points with a line. If it's discrete, we're not going to connect those points. We're just going to plot them and then leave them the way they are. Is that it?
No, we got some examples to do.
I meant on that particular slide.
I got nothing else to add, sorry. So -2, -1, 0, 1, and 2, your domains are going to stay the same, just like we've been doing in class. We're going to put those inputs into the x plus 3 expression. -2 plus 3 will give us an output of 1, and our ordered pair would be -2, 1. Good.
Then we plug in a -1. So -1 plus 3, you're just plugging it in for x in your function. It gives me an answer of 2. So I have a -1, 2 for my ordered pairs.
I get 0 plus 3.
I try to give you the easy ones.
I know. 3, 0, 3. Right on that x or y axis, sorry.
And usually if you've been doing 3 or 4 of them, you should start to notice a pattern in your y's. That way you kind of know you're on the right track. Plug in a 1. So 1 plus 3 is 4. So now I have the point 1, 4.
And surprise, surprise, 2 plus 3 is 5. Ordered pair is 2, 5. Now we're going to graph. So -2, 1 is left 2, up 1. -1 is left 1, up 2. 0, 3, coming across the y-axis right there. Nice job. 1, 4 is right 1, up 4. And then right 2, up 5. Is it continuous, Mr. McKenzie? Should we draw that line?
I would say yes, because we can plug in anything we need to for x and can get a y out of it.
We don't know a real-world situation to stop us from connecting it, so we will.
So as you're plotting those points, if you notice 1 doesn't quite fall in line with the rest, that's a good giveaway to go back and check your math as you were plugging in your x's to get your y's, and you might have made a mistake someplace.
Last example. -2 is going in for x, So negative 2 times 2 minus 1, or plus the negative 1, gives me a negative 4 plus 1, which is a negative 5. Ordered pair is negative 2, negative 5. Ooh, third quadrant.
All right, plugging in a negative 1, so 2 times x of negative 1 plus our negative 1, since we know we can make it adding the opposite there. Negative 2 times negative 1 is negative 2, plus 1 is negative 3. So I have the point negative 1, negative 3.
Oh, I get 0 again. 0 plus a negative 1
I'm still writing it out.
is negative 1. 0, negative 1.
Then I plug in a positive 1, so 2 times 1 is 2, plus negative 1 is a positive 1. So I have 1, 1. And you'll notice that our y values are increasing by 2 each time. So we kind of know what we should expect for our next one.
2 times 2 is 4. Plus a negative 1 is positive 3. 2, 3 is our ordered pair.
I don't know why it's not writing for me.
Time to graph. Left 2, down, left 2, down 5.
Oh, sorry. I read it backwards. Negative 2, negative 5. I do know how to graph points, I promise.
Negative 1, down 3. 0, negative 1. 1, positive 1. 2, positive 3. There we go.
And again, we don't know anything that would tell us that we can't assume that there are points in between. So as straight as you can, connect those points. Make sure your arrows extend all the way out through the sides of your coordinate grid and put those arrowheads on it to remind us that those points could keep going. If we were to plug in more x's, we would get even more points that we could be plotting.
And we'll see you tomorrow in class.